bien ahí?
Sí, perfecto.
¿Se ve bien? Acá abajo se ve el lapicito. ¿O no?
Sí, sí, se
Ah,
ve.
bien. No, porque a veces tengo problemas con la resolución y la relación de aspecto. Bueno, ¿empezamos entonces?
Sí, adelante, por favor.
Um, are you already recording? Yes, perfect. Okay, please, if you have questions, just let me know at any moment. Well, I am going to talk about the Torus project and the transient universe. I will try to put this in context. And what I want to share with you is a story about anticipation. And not only that, but also a story about the triumph of the human intellect and the remarkable achievements of modern technology. Anticipation is a key idea in science. That's why I highlight this. So it started 1 billion years ago. Two black holes, each one with a mass roughly 30 times the mass of the sun, were spiraling around in a binary system and getting closer and closer. Just let me put this one more time. This is a simulation, okay, of two black holes. And what we see is the perturbation of the fabric of space-time, which is produced because these two objects are so massive and so compact, and they're moving so fast that they produce a perturbation in space-time. This perturbation travels away at the speed of light according to the general theory of relativity. So when these two masses are moving in a kind of spiral orbit, then they produce this perturbation, which has the form approximately of the wave, right? This is a representation in 2 dimensions, okay? So the final stage of this approach, it's what produces the strongest perturbation in space-time. So even if we cannot observe with our current technology the gravitational waves for the in-spiraling stage of the merger, we indeed can observe the part of the merger itself, which is a stronger wave. And after that, since a new black hole is formed, then there are no more gravitational waves. Okay, so this final wavefront travels at the speed of light. 100 years ago, this wavefront was reaching our solar neighborhood, and a new theory of gravity was emerging on Earth. This theory, the general theory of relativity, predicted the existence of gravitational waves. If we consider a linear perturbation, a first order perturbation of the Minkowski space, then it is quite easy to obtain, quite easy today, right? To obtain the equations of gravitational waves. And the theory predicts that if we have free-falling particles, then they should react to the gravitational wave. And it depends on the frequency of the wave. If we have, for example, imagine that the tips of my fingers are 2 test mass particles, right? And if a gravitational wave with a low frequency passes through them, right? Then the effect is something like this. But if we have a gravitational wave of a much higher frequency, then we can observe something like this, okay? So the distance between the two particles is modified according to what is predicted by general theory of relativity.
Marcelo,
Yes.
have a question. If you can put the video
Yes, of course.
here. Why does the amplitude increase? I expect by conservation of the angular momentum, the frequency increase, but why the amplitude of the wave?
The frequency is increasing because this system, you're right, the system is losing energy.
Hmm?
That's why the two black holes are getting closer and closer. And this energy which is dissipated from the system is in the form of gravitational waves. So the general theory of relativity predicts that if the system loses energy by irradiating gravitational waves, then the two objects will need to get closer with time. So the perturbation in the final stage of the merger is greater because the two objects, which are very compact and massive, are closer. So we have the strongest perturbation at this stage. And then the wave disappears because we have no more two objects, but one final black hole, or final object, which if it is, it has spherical symmetry, so it doesn't produce gravitational waves. So another interesting thing is that the final black hole has a mass which is different from the sum of the masses of the progenitor black holes. And this difference in the mass, which in the case that I mentioned, is about 2 or 3 solar masses, is transformed in gravitational energy. Okay.
Okay, thank you.
Well, so Poincaré suggested in 1905 the existence of a kind of waves that transmitted gravity. Then in 1915, Einstein formulated the general theory of relativity. And a month later, he wrote a paper trying to obtain the equations of these waves. However, the calculations are not straightforward, so he made some mistakes. Years later, Eddington wrote a paper where he analyzed the 3 types of waves that Einstein proposed in his paper. And he demonstrated that 2 of the 3 wave types were just mathematical artifacts and produced because of a framework, a coordinate system, which was not ideal for make these computations. But there was still one more wave type which could not be discarded by the Eddington paper. Some years later, Einstein and Rosen wrote a paper which originally was going to be named Are there any gravitational waves? Because Einstein was convinced that gravitational waves could not exist. However, he again made a mistake, and in the process of peer review of the paper, he realized on that and then changed the name of the paper to On the Gravitational Waves. So at that point, it was clear that the theory actually predicted the existence of gravitational waves. And in the 60s, some people tried to make experiments to detect these waves. For example, Weber made this device which consisted on 2 cylinders, which were supposed to vibrate when a gravitational wave passes through them. He claimed that he detected a gravitational wave, but this experiment was not reproducible. So it was not a clear consensus on this detection. We now know that it was not possible with this device to measure a gravitational wave at that time. In 1974, Hals and Taylor analyzed the data from this pulsar PSR B1913+16 using Arecibo data. And they realized that the times of the pulses changed with time. Analyzing this data, they discovered that the period of the pulsar was diminishing with time by few fractions of a second per year. However, if they consider that this pulsar is part of the binary system of 2 neutron stars, then it is possible to make a general relativity prediction of this change in the period. And this prediction fits very well the data with an amazing agreement. So this is considered an indirect demonstration of gravitational waves. But it also needs a direct measurement. So can we make direct measurements of gravitational waves? Well, it is supposed to be possible using, for example, this device, which is the Michelson interferometer. As you know, this device allows to measure very subtle variations in the distance between the mirrors, between the, for example, the beam splitter and the test mass at the end. So if you can see the little pencil here, the device consists of a laser emitter, a beam splitter that splits the laser light into 2 beams, and this beam passes through a glass, right? It is reflected in a mirror at the end, which if you see it, it is transparent, but it is a mirror for laser light. There is an amplification of the power of the laser in this part, and also in this part. And if the distance between this test mass at the end of the device and this another test mass at the other end of the arm, if those distances are the same, then we have a purely destructive interference pattern in the photo detector, and we should not see any detection here. However, if you slightly move one of these mirrors, then it is possible to see the pattern of the interference pattern here. So this is the basic principle of the use of an interferometer to detect gravitational waves, because if we have the situation in which a gravitational wave passes through this device, then these test masses are expected to move, right? And then a pattern should appear here. Maybe it is more easy to understand with this animation. It is vastly exaggerated, of course. We see a variation of the mirrors because of the gravitational wave, and this produces the interference pattern. There is a trick here, which is that if the gravitational wave, which is a perturbation of space-time, produces a compression and stretching of the space, then the wavelength of the light will also be affected. So the distance between the mirrors will change in a fraction, which is the same fraction of change of the wavelength of the laser light. However, we know also that the velocity of the light is always constant. So if this is the case, then the light will need to travel a different distance at the same velocity. So this is the origin of the interference pattern in the photo detector. Okay. All right. These are the mirrors in one of the gravitational wave observatories. It is a very complex system because it is a requirement to make a measurement that this mirror, the mirror at the bottom, is completely or as isolated as possible from the vibrations of the surface of the Earth. There are many vibrations produced by seismic activity or human activity, industrial activity. Even the waves in the ocean produce vibrations. So this very complex system is supposed to isolate this mirror from all the vibrations that we see on the surface of the Earth. Well, there is a problem because this mirror is intended to reflect the laser light. There are many sources of noise in this system, mainly quantum noise, thermal noise, and gravitational noise. So the quantum noise is produced because in the laser light, since we are making very precise measurements, in the laser light, it is important the fact that light is made of photons. So the time intervals between the collisions of the photons with the mirror is important here. So in order to diminish the quantum noise, we need to use a more powerful laser beam. The problem is that if we use a powerful laser beam, then it is hitting the mirror and it is actually pushing the mirror. So it produces another type of vibration. In order to solve this, we can make a thicker mirror, a heavier mirror, but the problem is that a mirror which is larger will also have thermal noise because of the material of the mirror. So there are many problems, and the combination of the intents to solve these problems is what determines the design of the device. So we have here at high frequencies the quantum noise. We have here the gravitational noise, which is produced by the vibrations on the surface of the Earth, and we have in this part the contribution of the thermal noise.
Marcelo, I can interview you, please.
Yes, of course.
This noise is that they called as in a detection as a terrestrial detection, or what? Because they have different kind of detections. For example, black hole, or neutron star black hole. But sometimes they use terrestrial to describe a detection.
Yes, a terrestrial detection is something that happens on Earth that produces a vibration and it's not produced by gravitational wave. Yes, but we are not talking here about detections, signals, extraordinary signals, but about the noise, right? This part is the noise from the vibrations which are constantly happening on the surface of the Earth.
Okay.
Right. This principle that we saw with the interferometer is applied to several observatories of gravitational waves. For example, the LIGO observatories. LIGO stands for Laser Interferometer Gravitational Observatory. There are two of these devices, one in Hanford, USA, and another in Livingston, in the States also. If you look closely, you can see here, can you see some lines, which are the arms of the interferometers? Here is the other one. They are very large. They have 4 kilometers on each of their arms. And these two are not the only interferometers. The problem is that we need to place many of these devices in order to have a better orientation of the origin of the gravitational wave. So these two observatories are separated by a distance of 1,900 kilometers. And then we have detectors on other parts of the world. For example, the GEO 600, which has arms of 600 meters, which is located in Germany, and the Virgo detector, which is in Italy. There is a plan for the establishment of a new detector very similar to the Hanford detector in India, and the Kagra detector in Japan that has just started observations recently. So as the devices are improved with time, it is possible to reach larger distances and new systems, okay? So the volume of the universe that we can observe, which is actually the local universe, is increased when we can improve the devices. As you can see in this plot, we can reach a region which covers several galaxies, and we can see even the large scale structure of the universe here. So if we use a larger volume, we have more probability of detecting major events. The theory predicts two polarizations for the gravitational waves, which is the plus polarization and the X polarization. And it is produced by the orientation of the plane of the orbit of the two compact objects that give rise to the merger. So for example, in the plus polarization, imagine that we have here the L shape of a detector. Yes, the test masses here. Can you see me? Well, in the plus detector, the effect is something like this. Okay, it has the shape of a plus, right? Something like this. And then in the X polarization, the effect is different and is something like this. Imagine a circular set of test masses, which make something like this in the X shape. So if we consider the two test masses, the motion is like this. Of course, in most of the cases, we have a combination of these two polarizations, because the orbit is not just face on or edge on in the sky. So we have a combination, and the effect is something similar to this. Okay. So the important thing here is that we have two limitations, two very important limitations to obtain the direction of the origin of the gravitational waves. One is the design of the detector, which for example has an L shape. If we have, for example, the origin in this direction here, then it is the maximum sensitivity of the device. And here we have a blind spot, and here we have also another blind spot, right? This is, for example, the sensitivity pattern for the antenna, for antenna like LIGO with an L-shaped detector. And these are representations of the plus and X polarization. So we have a combination of these two things, or three things. And as a result, we cannot exactly know what is the exact location on the sky of the origin of the gravitational wave. There are many sources of gravitational waves. In a similar way to the electromagnetic spectrum, we have a gravitational radiation spectrum. It basically depends on the frequency of the objects that are spinning to produce the gravitational wave. And we need different kinds of detectors to observe different frequencies. For example, with terrestrial interferometers, we can observe frequencies of the order of 1 second. And if we want to observe lower frequencies, we need larger arms for the detector, and then we have to build interferometers on space. For example, the project LISA, which is a detector with a triangle shape, 3 detectors instead of 2. And the separation between the test masses, which are on space, is more or less 6 times the diameter of the Earth. So the length of these arms is much more larger. So at different frequencies, we can observe different astrophysical phenomena. For example, binary compact inspirals. Here, at approximately between 1 and 10 Hertz, we find the mergers of black holes or neutron stars, or black hole and neutron stars. And what we have, do you remember this? The white line, which is, oh, I'm sorry. The white line, which is the combination of all the sources of noise, is the sensitivity of the device, right? And I forgot to say that this, in the y-axis, we measure the strain, the so-called strain, which is the fractional variation in the distance between the 2 test masses produced by the movement of one of them. Did I explain myself right about the strain? I want to make sure about this. We have the distance between 2 test masses. Let's call it L. And we have a variation in this distance. Let's call it delta L. And we define the ratio of delta L over L. This is the strain, right? So, for example, in the LIGO interferometer, which has a value of L of 4 kilometers, it is possible to measure a value of delta L of 10 to the power of minus 20, for example, meters. That is a very precise measurement, because the variation in the distance between the 2 test masses is equivalent to a fraction of the size of the nucleus of an atom. So it's very small. Then I wanted to show you that in this plot, the sensitivity curve is something like this, right? So if an event is above this curve, then it is possible to observe it. And if it is below the curve, then it is lost in the noise. So as gravitational wave observatories are getting improved, this curve goes down, right? Because it is more sensitive, right? And if we put observatories on space, we can go to lower frequencies with sensitivity curves like this, for example, for LISA, right? Well, so this opens a new window to the universe when where we combine the information from gravitational waves and the information from electromagnetic waves. And this is the rest of the talk. Why we need to observe electromagnetic radiation? Because from the merger of 2 black holes, it's not expected to observe light, for example. But there is a model, which is the kilonova, which happens when we have 2 neutron stars that are inspiraling and finally merge. So in this case, when the 2 neutron stars collide, yes, there is ejecta of material which is very rich in neutrons, and this produces light which is according to the theory, actually observable, right? So kilonovas are supposed to have a luminosity 1,000 times the luminosity of novas, and that is the origin of the word kilonova. The theory predicted these events for a long time, and it was observed for the first time in 2017. Kilonovas are responsible for the production of most of the heavier elements that we know. For example, we know that from Big Bang nucleosynthesis, most of the hydrogen and helium and some lithium is produced. Then the next elements, here we have the mass number in the x-axis. The next elements are produced by stars, and the elements around a mass number of 56, which is the mass number of iron, are produced by supernovae. But in order to produce heavier elements, we need different mechanisms from supernova, stars, or even Big Bang nucleosynthesis. These conditions are fulfilled, supposedly, in a kilonova event, because we need a very neutron-rich environment, which is also dense, to produce these elements. And this is made through the so-called air process, which is short for rapid neutron capture process, which consists in the following, basically. We have a nucleus of an atom in a neutron-rich environment where neutrons are constantly merging the nucleus. There are many collisions, right? So with these collisions, neutrons get into the nucleus of the atoms. There is another process, which is the beta decay, which transforms neutrons into protons. So the combination of these two processes, the air process and the beta decay, gives us as the result the production of heavier elements than iron. So what we need is that the time scale for the R process is a little bit lesser than the time scale for the beta decay. So for example, kilonovas are responsible for the production of gold. And we know this because in the observation of the kilonova that we have observed, I'm going to talk to you about this in a minute. If we observe the spectrum of this event, then we can confirm that these processes are taking part in the kilonova event. This is a schematic representation of the kilonova. Here we have the final black hole, and the two light blue objects are the two neutron stars, which give rise to the central black hole. So there are two preferential directions. The direction of the jet, which is produced by strong magnetic fields, and the direction in the plane of the original orbit of the two neutron stars, which in the final stage of the merger give away ejectas of material. So this material, a time of the order of days after the merger event, produce brightness in this region. And at larger time scales and at larger distances, some emission is produced in radio, for example. So if we observe the light curves on different bands and on different regions of the electromagnetic spectrum, we can confirm this model. Some years ago, we started a project called TOROS, which means Transient Observatory Robotic of the South, which is a telescope dedicated for the following up of gravitational wave alerts. So it is very important to have observations of both gravitational waves and electromagnetic radiation, because with the combination of this information, we can constrain models for the kilonova event. The Toros project is located on Cerro Macón in the Salto province, which is also part of the Atacama Plateau, right? In a matter of fact, it is at the approximately the same latitude than the Amazonas mountain, right? It is quite close, but on the Argentine side. This site was a candidate for the installation of the extremely large telescope of ESO, which finally went to Amazonas. But we have been trying to develop an astronomical, a set of astronomical facilities in this site, which is which is indeed very, very good for the sky conditions. Today we have roads, for example, the supply of energy by solar panels, connection of internet, etc. The first Toros workshop was made on 2013. I remember that Gabriela Gonzalez was participating from this workshop, and people asked her about how confident were LIGO collaboration about the detection of gravitational waves. And she said that the detection could happen at any moment, tonight, for example, or in the next years, or in the next decades, but eventually we will witness the discovery of gravitational waves, and that happened 2 years after that.
Marcelo?
There was a pilot for the Toros project.
Sorry? It's left 30 seconds, so maybe we can close this meeting, and if you can enter again with the same link,
Okay.
please.